Hello, everyone, and welcome to this webinar where we'll be talking about turning web pages into data with Wolfram Language. Hope you're all doing well. And today we'll be doing a lot of, we'll be getting a lot of data from web pages. We'll be talking about why we want to do that, and once we get the data, what do we want to do with it? So, what we'll be covering today is the what and the why of turning web pages into data. First, what it is, and second, why we want to do it. Broadly speaking, we'll be covering two different methods of getting data from web pages. One is sending requests to the servers that are hosting the web pages, just asking for the content, which we'll be able to get in a text format. And once we have a text format, obviously we can slice it in different ways to get the information we want. And the second most more kind of complex, kind of more interesting way is automating web browsers. Where we'll be starting an instance of either Chrome or Firefox, and we'll be controlling that browser via Wolfram language code. And as you will see later on in the examples, that's quite a powerful tool to have because it allows you to do a lot of cool things. I mean, browsers in themselves are very sophisticated pieces of software that are capable of a lot. And with Wolfram language, we are able to kind of piggyback on the functionality that is built into browsers. We'll also be discussing some different methodologies, uh, sending asynchronous requests, parsing structured responses, either parsing XML objects, parsing normal text. We'll get into all of it. So this is, broadly speaking, the plan for the session. So let's get into it. Let's just talk about extracting data. What does that entail, and why would we want to do it? So extracting data involves obviously fetching the web page's content and parsing it to retrieve specific information. In most cases, that information is text, could be images, could be links, could be files, could be anything. The reason why we're able to do that consistently and reliably and on a large scale is because web pages typically have a consistent format. So every time you open a web page in your browser, you're seeing your browser is rendering an HTML file. And HTML is just a markup language that has a not a perfectly consistent, but consistent enough structure that we're able to leverage that and navigate that structure programmatically. So why would we want to do it? The main advantage is that we are able to scale up. If we write, let's say, a piece of Wolfram language code that gets data from one web page, we can apply it to 10 different web pages. Because if it's just about one web page, we can just go to the web page, copy and paste the contents we're interested in, just pop it in our notebook. That's absolutely fine. But if we want to do it to 10, 50, 100, 1000, then that's when doing it programmatically really gives us an advantage. But why do we want data in the first place? Well, the main reason in the context of this webinar why we want to get data from web pages is that once we got it in our Wolfram language notebook, we can use any of the, at this moment in time, any of the over 6,000 functions in Wolfram language to do interesting things with the data, whether it's to visualize it, whether it's to do some statistical analysis, whether it's to publish it somewhere else. Once we have the data in our notebook, we can treat it as any other data you have in your notebooks. So it opens up a lot of possibilities for your data once you can reliably import it in Wolfram. So we'll start with the very basics. We'll start with importing web pages as text and parsing that text to get the information we want. Just before we get into that, just a small aside to talk about robots.txt. Robots.txt is a special text file that pretty much every website has that indicates whether that website allows people to get data automatically or not. So it's a good practice before you start writing Wolfram language or any other programming language to collect a lot of data automatically, it's a good idea to check out the website's robots.txt, which is usually located at the root of the website. So if the website is example.com, it will be www.example.com/robots.txt, which contains structured information of which parts of the website are accessible to web scrapers and which parts are not. Um, it's very good practice to follow the information in robots.txt, but also to use common sense. I mean, if you are, for example, if you're dealing with a small web page, obviously don't send 500 requests per second, because that's going to cause a lot of load for the server and may ruin the experience for other people trying to visit the website. Just use common sense. Don't make other people's lives difficult. Um, but yeah, so let's get into it. So we are going to start with a very simple web page that we are going to extract some information from. So before I get into the code, let me show you what the web page looks like. Just give me a second. Laptops. Just opening the web page in my browser just to show you what it looks like before we start interacting with it via code. So what we are looking for is just a normal web page that looks like an online store, e-commerce website that is selling a lot of different things. In this case, we are navigating to the laptop section. You can see there are a lot of laptops. Now, this is a fake web page. It's a page built specifically for people to practice their, as you can see, web scrape is called web scraper. So it's built specifically for people to practice their web scraping. So none of the information is real. It is just yeah, it's meant to mimic the structure of what a real e-commerce website would be. So what we are going to do now, what we're going to start with, is we want to get a list of all the products that are on this web page. As you can see, there's quite a lot of them uh, right now, probably about 100. So again, I could probably just copy and paste the names, but I want to do it programmatically. So let's close the web page and let's see what the code looks like. So the first thing, the most simple way, I should say, of getting of requesting a web page from a server is using the import function. Now, you probably recognize the import function from importing local files on your machine. So if you have a CSV file, you pass it to import and you get it in a dataset structure, for example. But import is equally capable of importing data from external sources, in this case web pages, and it works in pretty much the same way. Instead of passing a local path name to a file, you pass the website that you want to import, and then you specify that you want to import the file as text. So let's do that. So I'm suppressing the output because it's quite long, but let me show you what that looks like. What we are seeing is just one huge piece of text, one big string, that is essentially the full HTML file that we just saw in the browser. Okay, so we have this huge piece of text, but obviously we are only interested in a very small section of it. We are only interested in the products that are listed on the storefront. We don't care about the menus. We don't care pretty much about anything else on that web page. So what we are going to do now, and perhaps I should open back the browser just to show you what we are doing. Let's come back here. Oh, why is it not loading now? Okay. So we're interested in getting all of the products, right? So what we need to do is we need to identify where in the HTML those products live. So there are a few different ways of doing that, but perhaps the most kind of convenient way is once you have the web page open in the browser, depending on which browser you use, that will look slightly different. But I'm using, what am I using? I'm using Microsoft Edge at the moment. So this is how it looks like for me. I right click anywhere on the web page and I select inspect. Again, depending on the web browser you use, this might be called inspect elements or web inspector or something else. but it's pretty much the same idea. If you're using a different browser and you can't find it, feel free to leave a comment in the chat, and I'll try to help you out with that. But anyway, once you get your web inspector open, so on my screen you can see it on the right hand side, I have this menu which shows me all the essentially the full HTML structure of the web page. So what I want to do is I want to use that selector tool on the top left corner of my inspector menu. And again, if you're using Firefox, this will be somewhere else, but it will look roughly the same. And it says select an element in the page to inspect it, which is what we're going to do. So we can, once we select that tool, when we point to different parts of the web page, we see the HTML associated with those. So instead of trying to read that huge piece of text that is the full HTML, we point at the parts that we are interested in, and that tells us where they live, essentially. So let's say we are interested in this full title here, instead of, because the titles themselves are truncated and we want the full titles of the products. So we point to one of them and we click on it, and that highlights the section of the HTML where that element lives. So you see the description for the first product lives in this piece of HTML here. We have a p tag with class description, card text, and some other attributes. And this HTML tag contains the description. Once we know that, we can go back to our code. And we can use, so there are two different ways of parsing strings in Wolfram language. And they're both functionally the same with some very tiny differences. But if you are, let me make this a bit bigger, actually. Might be too small to read. Hopefully this is better. So if you have mainly used Wolfram language, you are probably more familiar with the string expression way of parsing strings. And if you are coming from any other language, you'll probably be familiar with regular expressions. So the idea behind string expressions and regular expressions is roughly the same. You have a piece of text, a string, and you're looking for some common patterns within that string. So coming back to what we're trying to do today is we are trying to identify the elements in the HTML where the information that we're interested in lives. As we identified in our browser, it lives in this kind of HTML tag, which is p class description card text. Now this here is a string expression syntax, which if you're not familiar with it, I kind of encourage you to read the documentation, but I will try to explain it in plain English what this piece of code does. We're saying that the part of the HTML we're interested in starts with this p class description and text, and then we are taking it starts with this p class description text. It ends when the p tag is closed. So again, if you know if you have some HTML experience, you recognize tags are open and closed. But essentially, what we are saying is we want everything that is between the opening of the tag and the closing of the tag. So let's see what that looks like. And what we get by applying string cases and string expression is a list of essentially all the different pieces of the string that match our string expression. In this case, because we selected the right p class, that is just a list of all the products on the web page, which is, let's see, how many products do we have? I have 117 products. Again, we can do the same thing with regular expressions. And here I've done a bit of a better job with cleaning up the actual text. So we have, again, we essentially have a list of all the different products. Okay, which if we do length on it should give us the same length because we're doing the same thing. Let me just double check for sanity. Yep, it's 117. So whether you do it with string expression or regular expression, it's pretty much, as I say, they're 95% identical in functionality. The syntax is quite different, so it's mostly a matter of preference. But the basic idea is we start with a huge piece of text and we extract the parts of it that are relevant to us. So that's the most basic way. Now, it's not a very powerful way. As you saw, we need to go in the browser, see where in the structure the code that we're interested in is. We have to import it as one huge chunk of text. It doesn't seem like a very elegant solution, and it's not. But the benefit of it is that it's very, very simple. Just pass the website to import, say that you want the text, and you have it. Um, Import is kind of the high level function that allows you to import web pages. There is more manual way of getting the text from a web page, and that is using the URL read function. Um, what URL read does is instead of giving you just the text, it gives you the full HTTP response. Without going into too much detail into what an HTTP response is, we can say simply that it contains the text of the web page, the content of the web page, but it also contains a lot of other things, things related to how the server responded to the request, what request was sent, and so on. So knowing about URL read, so here we're sending URL read to the same web page that we used in the previous example, and we are saving the HTTP response in this variable. So as I mentioned, this variable has the text, but it also has a lot of other things. If we just want the text, we can get the body property, and as you will see, this is exactly the same HTML as we got from the import function. But now we can, because we have the full HTTP response, we can also query um, other properties of the HTTP response. In this case, the headers. This is very useful if you're trying to understand better how the server responds to your request. But for simple kind of importing the web page as text, you can pretty much always use import, and it will be easier and it will give you the same result. Okay, so before we move to the kind of more complicated functionality, let's see how we can use even simple import just to do something a bit more interesting than collecting something from a single web page. So what we're going to do in this example is we are going to visit the websites of a few businesses based in the UK. Specifically, we are going to use their contact pages, and we're going to try to extract their phone numbers from the web pages. So here we start with a contact pages variable, which is just a list of associations where each key in the association is the business name and the value is their website. So here we're dealing with Apple, Barclays, Monzo, and Every. Again, just very big, well-recognized businesses that are either based in the UK or have offices in the UK. So let's define that. The next thing we're going to do is we're going to define a little helper function called get contact details. And essentially what we're going to do inside this function is we are going to import the web page, so the values of each association. We're going to get the text, and we're going to, in that text, we're going to try to find this pattern. So again, this is a regular expression pattern. If you haven't used regular expressions before, this might look a bit weird to say the least, but essentially what we are looking at is just common ways that people structure their phone numbers. So we have 4 digits followed by either a space or a dash, then followed by 3 digits, and so on. So it's just a very kind of it tries to capture several different ways in which UK phone numbers specifically are formatted. So let's define our function and let's apply the function to um, each page in our dataset. So we can see that for each business, we have a list of phone numbers. So we were able on the Apple web page, we were able to find 5 different phone numbers that matched this expression, and on the rest of them, we only found one. Again, very very simple example, but it kind of shows you that even with just simple import statements and regular expressions, you are able to collect some data from different web pages. And now the good thing about it is, again, this example only includes 4 businesses. But now that we have it working, let's say we wanted to get the phone numbers of more web pages. All we need to do is go back to our contact pages and just define our next businesses. I can't think of any UK business at the moment, but the idea is you can add more to this list, run the function again, and immediately you have the phone numbers. If your code is able to recognize them, you have the phone numbers of them again. No need to visit the web page and copy and paste it yourself. Okay, so let's talk about structured responses and how to parse those. So far we have been looking at simple text, a huge piece of string, essentially. Um, what we are able to do is we can import web pages not only as text, but as, in this case, XML objects. So if you're not familiar with XML, stands for Extended Markup Language, I believe. It's just a file format that is used. Well, it was used very commonly in web development previously, not so much now, but it still persists. And the advantage of XML is that it is a very structured format. So unlike strings, which are just normal text, they don't necessarily follow any structure. XML objects are very structured. Now, the disadvantage of XML is that it's no longer very common. Um, so you wouldn't be able to apply this method to every single web page you encounter. But for web pages that do have XML objects, you're able to import them and do some cool kind of navigating of the XML structure. So one set of websites that still use XML quite a lot are news websites. So I say every, but not every, but 95% of news websites have sitemaps, which essentially is an XML object listing all the articles that they have published recently. So, and actually, the reason why most news websites have XML files listing all the articles they have is so that scrapers by Google, for example, can easily index them, and they can include them on the Google search results. So this is how, if you think about it, this is how Google is able to surface. Let's say you search for what is happening in anywhere in the world right now, and you get some relevant news. Well, you're able to get that relevant news because Google has navigated in, let's say, the BBC's sitemap, and it has extracted the information it needs from the XML object. So let's do that ourselves. Sitemaps are available to everyone, not just Google. So let's see how we can do it ourselves. So what we have here is BBC's sitemap website, which ends in XML. So again, we are using import, but this time instead of importing our website as text, we want to import it as XML object. So that's the only change. And as you can see, obviously, instead of getting text, now we have this huge object, 2.8 megabytes in memory. And you can see that it's an XML object. The next thing to do is actually start navigating the structure. And again, this is how do we know where to navigate? Well, we inspect the actual XML object and we see where the URLs are located. And once we see where, or I say the URLs in this case, but any information that we are interested in is located. And we can see that we are interested, we want to get all the URLs leading to news articles on the BBC website. So you can see one right here at the top of the XML object. So we can immediately see where it is located. It's located in an XML element that starts with a location or loc. Then it has an empty list. And then the third element in that XML element is the actual URL that we are interested in. So if we want to extract all of those XML elements, we just need to replicate the structure and pass it to the cases function. So we are saying get the cases from the BBC sitemap, which is where we saved our XML object. Get the cases with this specific structure. So XML element, location is the first argument. This underscore in Wolfram language stands for any or anything. So the second element could be anything. And the third element is a list that contains the URL. And we are saying from this structure, we want only the URL. We don't care about the location. We don't care about the second element. So when we're on that, hopefully we should get a list of all the links from the BBC sitemap that lead to BBC articles. So let's see how many we've got. We have 990. So again, so this is now is becoming more obvious why we want to do these things automatically. We definitely don't want to copy and paste 990 elements, and especially when it's a structured object like XML, which we are able to navigate very simply with one line of code in Wolfram language, and we're able to get all of the links. So um, also, the next thing we're going to do is we are going to also extract the headlines. So far we only have the links to the articles, but the XML object also contains all the headlines. So we do it in a very similar way. We find the place in the XML object where the headlines live. We look how it's structured and we replicate that structure in our cases function. So again, very similar idea. Let's run that. And next, we are kind of taking both the headlines and the URLs and we're putting them in a single database. So now we have a very simple database of two columns where one of the columns is the headlines and the other is the URL. Cool. And then once we have that information, we can start doing things with it in Wolfram language. For example, um, we can generate a word cloud that gives us a nice visualization of all the headlines that we were able to get from the sitemap. So that gives us a very nice visualization to see what are the topics that are mentioned most um, in the last 990 articles that the BBC has published. News, obviously, being the top. Transfer, probably related to football. India is quite big. It's been in the news recently, and a lot of different things that you can see on the word cloud. Another cool thing we can do is we can have a little fun with the LLM functionalities that are built in the Wolfram language. So here we are using LLM example function. So what LLM example function does is it's a small scale, very basic training of the LLMs where you provide a task to an LLM and you give it some examples of how to accomplish that task. So in our case, we're saying emojify, which is an LLM example function, and our LLM example function will do the following thing. It will summarize the news articles using emojis. So after that, we provide a few examples to the LLM to learn from. So if it's red wind warning issued from a storm, it should summarize it something like this. If it's about the rail network, it should summarize it like this, and so on. So essentially, we're giving it a few headlines and we're telling it what an emoji summary of those headlines might look like. Once we have that LLM example function, we can pass it new headlines. So these ones are just example ones. So let's take 5 random ones from the BBC today, and let's pass it to the LLM to summarize as emojis. And let's see how well it does. So this is obviously some football transfer news. This is possibly a tsunami. Seems like a big wave and a scared emoji. Tree and a chef, possibly something about vegetarianism would be my guess. I'm not sure. So you can, again, this is nothing serious, nothing too useful, but just a little play around with Wolfram Language's LLM functions. But the basic idea is that once we have the data, so here we have, well, given, granted, very basic data, we just have headlines and we have URLs. There's not that much we can do with that limited information, but we can have a bit of fun with it. We can kind of visualize the headlines and so on. But the main point is once you have the data in Wolfram language, you're able to do anything you want with it. So the next thing I want to talk to you about is asynchronous requests. I'll explain what that means. And that is basically if you have a big list of web pages that you want to visit, more than, let's say, 10, if you pass them to import, you can just store them in a list and pass them to import. But what that means is that import is going to visit them one by one. So import is going to visit the first page, import it, close it, visit the second page, import it, close it. So that obviously takes a lot of time, especially if you have a lot of URLs. So essentially what we would like to do instead of visiting them sequentially is to spawn, let's say, 10 different processes that each go to a website, collect it, and so on. So instead of just having one worker, so to speak, we can create a lot. And asynchronous requests are very kind of common in getting web pages from data. So let's see how they work in Wolfram language. So we'll stay with the BBC example for a little bit, but now instead of looking at their sitemap, we're going to look at their front page. So again, we're starting with a simple import. We're passing the main BBC website. And in this case, instead of saying text or XML object, we're saying we want the hyperlinks. So that's another argument you can pass to import when you're getting data from a web page. Instead of getting the whole, the full HTML file as a text, you can say to import that you only want the hyperlinks. You only want the URLs that are contained in the HTML. So under the hood, there is some essentially string parsing that goes on, but that means you are able to get all the hyperlinks located on the BBC homepage. So what we're actually interested in is all the news articles that are on the BBC homepage. But the BBC homepage includes more links than just the article. So pretty much every menu option is a link. As you can see, actually the first 10 or 20 just refer to the different categories on the BBC website. They're not actual news articles. So what do we need to do to get the news articles? Well, we can do, again, very simple string cleaning. And in this case, it's probably the most simple string cleaning we have done. Essentially, we're saying we want all the hyperlinks that start with this pattern. We want all the hyperlinks that start with bbc.com/news/articles/something. In regular expressions, this dot asterisk that you see here stands for any symbol. Basically any symbol. So when we run that, we have a much more manageable list of about 20, maybe 30. Let's see how many articles they have on their front page. Article links of 41. We have 41 articles that we want to do something with. Now let's see what we're going to do with them. Essentially, what we want to do with them is get the actual text of the articles. And as we saw, we have 41 links. Now we can pass this BBC article links list to import, and then try to try to parse the text of each one. But as I mentioned, those 41 articles will be processed one by import. So what we want to do is we want to process as many of them as we can in parallel. And to do that, we use a function called URL submit. There is a lot of parallel computation functions in Wolfram language. So if you're doing any other type of computation, uh, do check out parallel evaluate, parallel table, and functions like that. In the cases of web requests specifically, the function is called URL submit. Now, the syntax of URL submit is a bit more complicated than the plain import function, because we need to tell URL submit how to handle different events. And we're saying in this case, handle the event called task finished. So every time a task is finished, we want to append something to this empty variable that we initialize here. And what that something is again a piece of string cleaning, which essentially gets the article's text and appends it to the list that we have here. So let's define our empty list and let's run URL submit with all 41 articles on the BBC front page. So as you can see, it takes a while. After all, we're getting 41 web pages essentially. But the good thing about URL submit is that it gives you these kind of indications for each of the tasks. And obviously, the main advantage is that each task is able to run independently of any other task. And that's perfect for workflows like this, where the content of one article doesn't depend on the content of any other article, so they can run in parallel. So let's see how many articles we have collected. And obviously 41, because we had 41 links. And again, we can do a simple word cloud, but this time instead of just only using the headlines, we are using the full content of the articles. Again, we see kind of similar idea, but it's just a visual indication of what has been talked about in the news, in this case today, or whatever is on the front page of the BBC website. I'm guessing it's all from today. So things like said and people are just very common words, nothing interesting there. Trump, obviously, the UK, June. But yeah, again, a little visual indication to give you an idea of what has been in the news. Now now that we have the full bodies of the articles and not just the headlines and the URLs, we can start doing slightly more interesting things with that information. So we can use text cases, which is a built-in Wolfram language function that tries to locate from a simple string. It tries to locate whether some entities were mentioned. In this case, we are looking for country entities. So what we are doing is we are passing all of the BBC articles, the full body of them, and we are telling text cases to look for any mentions of countries and interpret those as actual Wolfram language entities. So essentially, this is the difference between having a string that says France and having entity country France. So this is just a simple string. It doesn't mean anything. But if you have a Wolfram language entity, Wolfram language knows a lot of things about entities, so you can immediately query things like population, and you get population. You're able to do computations with all the different properties. So it's very useful to store your information as Wolfram language entities. And here I'm just querying what is the full list of properties. So essentially, what does Wolfram language know about France? And these are all the different things you can query. You can get immediately the result in your notebook, and you can do computations with them. So you can see it's a formidable list. So this is why we are interested in which countries were mentioned in the BBC headlines, the BBC articles on the front page. So what this gives us is the list of all countries. Very cool. Let's keep going. What the first thing we want to do is we want to see which countries were the most frequently mentioned in the BBC front page as of now, as of the 16th of July at 3:40 p.m. UK time. So by far the most mentioned country today is the United States, followed by India and Cuba. It's quite interesting, and then all the rest are pretty much only mentioned a few times. So this again, it's not a visualization, but it gives us an idea of what's going on the BBC website without actually having to read it. Um, we can do again word cloud. By this point, you probably know that I quite like word clouds. So here we are doing word clouds specifically for the mentioned countries, where each word, the size of each word, is proportionate to how frequently the country is mentioned. So the U.S. being mentioned 122 times has the biggest text size in the word cloud, and so on. Again, just a simple visualization. We're just changing United States to US and United Kingdom to UK. Otherwise, their strings are too big, so United States takes up the whole width of the word cloud, which doesn't look very nice. Let's keep going with our computations. So we can construct a geo bubble chart, which similar to the word cloud, but just on a map. Um, for each country, it plots a bubble, and the size of the bubble is proportionate to how frequently that country is mentioned. So again, the easiest one to recognize is the US has the biggest bubble in the bubble chart because it's been mentioned 122 times. Then a country like the UK has been mentioned 29 times. And then you can kind of, again, just a different way of visualizing which countries are being mentioned today in the BBC. Um, Japan's been mentioned twice, and so on. Again, keeping with the word cloud idea, um, so this piece of code is going to take a little bit to actually execute. So while we are waiting for it to do its thing, I'll try to explain what it's doing because it's quite a horrendous piece of code that I wrote. I just wrote the first version of it. Just I was just curious if it's going to work, and it did. And then I never really rewrote it in a nice way. But let me try to explain what we are going to do with this code. So it's a helper function. It takes a list of articles and it does the following thing. So the first thing it does is it takes the top three. So essentially, it produces a list like this and it takes the top three countries. So in this case, it's going to take the United States, India, and Cuba. We are defining a list of unwanted words. So these are very common words that don't actually mean anything. And so we don't want them in our word cloud. So as you saw in one of our previous word clouds, there were words like said, for example. Now, obviously, that's going to be a very common word because it's people are just reporting what other people have said, but it doesn't really tell us anything about the underlying content. So we don't want that word. Uh, so yeah, we're just saying that this is the list of all the words that we don't want. Um, and then we are looping over each country in the top three. So the table function is a looping construct in Wolfram language. So we're saying for each country in the top three, generate a word cloud where you delete stop words. So this is the horrendous part of the code. But basically, if I try to explain it in simple English, where for each country we're creating a word cloud from all the articles that mention that country, and then the shape of the word cloud is going to be the shape of the country. Now, as I said that, I realize that's probably not very helpful, so let me just show you what the end output looks like. So essentially, our function generates three different word clouds, and each has the shape of the country. So the first one we can kind of recognize as the US. So the shape of the word cloud is the country itself, in this case, the US, and the words in the word cloud is all the words in the articles that mentioned that country. So in this case, it's all the words that mention the US. So if there was a BBC article mentioning India but not the US, it would not be included in this word cloud. So we are looking at all the words relevant to the US from today's articles, all the words from India uh, related related to India, or articles that mention India from today, and then Cuba. Um, Again, slightly nicer example now that we have a lot of data, which is still a lot. It's not really a lot of data. We only have 41 articles. A lot of data would be thousands and thousands of rows. But it's a nice proof of concept of different ways. Once you have the data, of different ways you can manipulate it. All right. So another cool thing that we're going to do before we move past the BBC example is we are going to create a semantic search index. What is a semantic search index? It's a bit difficult to explain quickly, and it's not really the topic of our conversation today. But what a semantic search index does is it takes a huge corpus of texts. Um, Again, in our case, it's 41 BBC articles, but it can be many, many more. And it stores that, stores, converts and stores all of that text in a vector database. And the advantage of storing it in a vector database is that it can be passed to an LLM, to AI, and then the AI is able to query that vector database to find relevant information. So in our use case, we are creating a semantic search index from all the BBC article bodies, so the content of all of the 41 BBC articles. We are creating a semantic search index that we will make available to the LLM. What that allows us to do is it allows us to ask questions about the information in that semantic search index. So by default, LLMs have a lot of information, a lot of knowledge built into them, but they don't necessarily have the latest information built into them. So because in this case we are dealing with the articles on the BBC's front page, it's pretty safe to say that ChatGPT, for example, without searching the web, is not going to have access to that information. So a semantic search index is it's a very simplified explanation, but it's essentially a way of giving the LLM access to that information. Once we do, we can start asking questions that are relevant to that information. So we saw that the top three countries were US, India, and Cuba. So we can ask a question like, why has Cuba been in the news recently? And again, if our LLM didn't have access to the semantic search index, then it wouldn't be able to answer that question in any meaningful way. And we can test this by running the same query without giving it access to the semantic search index. So just using LLM synthesize, why has Cuba been in the news recently? And as you can see, without the semantic search index, it's giving me information from 2023. But when we do have the semantic search index, we get a lot more relevant information. And we can ask different questions, like, because the Cuba one is quite depressing, we can say, what is the most positive piece of news recently? And again, using that database, it will be able to query. Oh, or it not. It might not. The context provided does not contain any positive news. Well, that is just the news business for you. But anyway, I hope you get the idea behind the semantic search index. You are able to ask information about the data in the semantic search index. Okay, cool. Now, getting to the more interesting part. So far we have been interacting. We have been requesting data from websites by simple Wolfram language functions. So we haven't had to deal with browsers at all. We simply send a request to the server saying basically, hey, can you give me the contents of your web page? And then the server provides it. Very nice, very lightweight, very powerful. But we can take it further. We can actually automate browsers. And there are just before I get into the actual functionality, let me just say a few words of why we might want to do that. One, it gives you more control over the content and how you navigate the web page, as you will see in some of the examples. Because when we send a simple request to a server, we're just saying, "Hey, give me the web page," and it gives you the web page. So there's no dynamic functionality included in that. When you're controlling a web browser, you can click buttons on the website, you can navigate to different parts, so you're more easily able to locate the information you need. But probably the most important advantage of using web browsers over simple requests is that a lot of web pages nowadays load content dynamically. So you visit a web page and it has a very simple structure. And once the web page recognizes that you're a browser, it loads a lot of, typically, it's a lot of JavaScript that queries different servers and loads the information. So if you send a simple HTTP request, you're going to get just the basic structure of the website. But then if you visit it via a browser, then the browser is going to load all the JavaScript, which is going to populate that structure with the information you actually need. So a lot of times you actually do need a web browser to get the information you need, because the server doesn't store it in a static format that it is able to give to you. Okay, so with that out of the way, let's see how automating web browsers works. The most simple, well, actually the only way, I say the most simple, like there are 10,000 ways, but the way to start a web browser session with Wolfram Language is by using the start web session function. And it takes a single argument, which is the web browser that you want to automate. In this case, I use Chrome. I think only Chrome and Firefox are supported. So unfortunately, if you're an Apple user and you really want to use Safari, for example, that's not currently supported. I hope it will be at some point, but in any case, Chrome and Firefox are pretty much 90% of the market anyway. I think even for people who do use Safari, they do have Chrome or Firefox installed just in case. So in this example, we're going to use Chrome. So let's evaluate this and see what happens. So as you can see, we get a Google Chrome, obviously, instance launched, and it's completely empty because so far we haven't told it to do anything. So start web session only starts the web session, as the name, excuse me, as the name suggests. It only starts the web session. It doesn't do anything with it. And the way we operate on that session is we store it in a variable. In this case, I'm storing it in the session variable, and then we do things on that variable. So because the variable contains the session, we can do things on it. It's a very kind of object-oriented way of thinking about it. So, okay, we've started our web session. We have it stored in session. So the next thing, and you're pretty much your best friend when it comes to automating web browser, is the web execute function. I highly recommend reading the documentation of the web execute function because it's very thorough and it's very useful. Um, but it just lists all of the different things you can do with web sessions. So let's start doing the basic things so we can kind of learn by example. So we are saying web execute on the session, on this session, and we are saying open page, which is one of the things you can do on sessions. And we're saying open page goes to example.com, which essentially means open example.com. So let's see how this works. So what I'm going to do is I'm going to keep my notebook on the left, and I will have the Chrome browser on the right. So you can see that when I evaluate the code, you can see what happens in the browser. You don't have to guess. So let's evaluate that function. And we can see that our browser has navigated to that web page. Pretty cool. Let's keep going. Again, we're using web execute on our session. This time we're not navigating to a web page, but we are locating elements within that within the web page that is currently open. Again, here we are back to HTML. So having some um, even basic knowledge about how HTML files are structured will go a long way in helping you, well, with any aspect really of getting web pages from data. But in this case, we are saying locate the elements with a tag h1. So tags in HTML look like this. You have h1, and then you have title, and then you close the tag. Just in case, for those of you who are not familiar with HTML, this is what we mean by tag, and this is what we can reference in our web execute function. So we're saying get us the tag, the h1 tag in the page. So what does that give us? It doesn't really give us the text. So the h1 tag is the title of the web page, which is example domain, and let's say that's what we're looking for. And we say give me the h1 tag. But as you can see, we're not getting example domain. We are getting a web element object that contains a web element object. To actually get the text that is contained within that object, we can query element text, and we can pass that actual web element object. So to do that, and we get the actual text that is contained within the h1 tag. So why doesn't locate elements give us the text directly? What else can we do with web element objects? Well, we can do a lot of things. We can hide the object. We can click on it. We can scroll it into view, and all sorts of different things. So getting its text is only one of the things that we can do on web element objects, and this is why we get the object itself, and then we say what we want to do with it. Okay, pretty cool. Let's keep going. We're using web execute on our session, and we're opening a different page. This time we are opening quotes2scrape.com. Again, it's one of those web pages that is made specifically to kind of train your web scraping skills. And what it is, it's a simple, very simple web page that contains just a lot of different quotations. So let's say that we want to get the quotes, obviously. So let's see what we're going to do. Again, pretty much the idea is we explore the structure of the HTML, we find where the quotes are, and then we try to represent that structure within our code. So in this case, the quotations are all in a span tag with a class text and another attribute called item prompt, which has a value of text. So the first thing we want to do is we want to collect all the span elements, which we can do with web execute, locate elements with tag span. Now, unfortunately, there are span tags that don't contain quotes. They contain different things, maybe the title, maybe the categories. So the next thing we need to do is get all of the spans that only contain our quotes. So what we're going to do, again, now it becomes slightly more complicated, but the principle is the same. We have web execute. So let's start from here. Actually, let's start reading the code from here. We have web execute on a session. We're looking at the element attribute. And the specific element attribute we're looking at is the class. So if we run that on a quotation, it's going to give us text. Essentially, we're saying for each of the span tags that we have, give me their class values. So because it's class equals to text, we're going to get the text. And we are saying that if the value matches text, because we know that this is where our quotations are. If the value matches text, then do the following, and the following is get the actual text, pass the element text, get it. And if the class is something different, which is where the tags would be, they would still be span elements, but they would have a different value for class. And we're saying if it's not text, then do nothing. And we're applying that to all the span tags. So hopefully that makes sense. Let me run the code. So what that gives us is a list of all the quotes on the front page. And we can kind of verify it very quickly visually. This is the same as this. So again, it's looking at the structure of the HTML and trying to represent that in code. So the next thing we're going to do is we're also going to get all the authors. Again, similar idea. I'm not going to go through all the quotes. And the next thing we're going to do is map the quotes to the authors. So this goes to Albert Einstein, and we can see that this goes to Albert Einstein. So we are now that we have the data, we are actually structuring it in Wolfram language, so we can kind of do things with it. And one thing we can do is to get a random quote and to frame it. So essentially, what this code does is it takes a random element from the list where we store our quotes, and it presents it in a nice way. So so this is our random quote of the day. So once we are done, one important thing to mention is that, as you can see, through all of our workflow, our web session is open. So our browser on the right keeps running. It's important to know that if you don't close it, then it's just going to stay there as a running process on your machine, which is not what you want. So once you're done with your Wolfram language code, a very good practice is just to call delete object and pass the session, which is just going to close the browser. Okay, so this was kind of the basic functionality of automating web browser, navigating to different web pages and locating different elements. So let's actually start applying these functions to do cool things essentially with Wolfram language. Um, Again, we're starting a web session. So a start web session takes a few options. The most important one is visible false, which means that if we don't pass it, we get a window on our desktop that we can see. But in many cases, especially once you have your code nailed down, you don't really want to see that window. You want the things to happen kind of in the background. So you can say visible false, which starts a web session but doesn't open any graphical user interface. But under the hood, it's pretty much the same. So again, we're starting a web session and we're starting to do things on it. We are opening a Wikipedia page about blood type distribution by country, and we are locating the table on it. Actually, let me show you what that web page looks like, just so you can see what we are dealing with in our code. Just see. So this is the, let me close this. This is the Wikipedia page that we are going to be visiting with our automated web browser, and we are interested in this table here. Um, it's a nice table. It has a lot of data in it, a lot of percentages, a lot of numbers, so on. So we're saying locate all the elements with the tag table. Here we're getting the second one just because on the Wikipedia page there is a table element somewhere else in the HTML that doesn't actually refer to any table. But in any case, the table that we're interested in is the second one on the web page. So this is what we're saying. Now we're doing our standard string cleaning. I'm not going to go into detail on all of this. If you're interested, you can kind of look at the code, but I can tell you what we are doing in effect. In effect, we are saying that we are essentially taking that raw table from Wikipedia and we are formatting it in a way that we'll be able to use it in Wolfram language. So all of this code here is string cleaning, and now we are again using the built-in interpreter to interpret these actual strings as country entities. Um, and finally, this is what our data will look like. So what are we looking at here? We're looking at all the countries in the European Union, or all the countries in Europe, actually. Um, and for each country, we have the proportion of people with a blood type in it. So 36.7 of the Albanian population has a blood type, 44% of Austrian population, and so on. So now this is a very nicely structured data set that we have in Wolfram language, and we can use our kind of geo visualization options to kind of present it in a much nicer way than the Wikipedia table does. um, because immediately, so for example, one interesting thing we can see is that Norway is actually quite an outlier. You can see how different its color is from pretty much everywhere else. And Ireland is an outlier from on the other direction. So we're able to spot things like that much more easily than if we were looking at. Oh, I close it, but we're able to spot things much more easily than we would just by looking at the table. So that's one of the advantages of getting the data in your Wolfram notebook and then doing different things with it. All right, let's keep going. This is quite a lengthy example. Um, I don't think I'll have time. Let me just see how long it is. I think I will just explain to you what we are trying to do and then just run all the code and just show you the end result because this is a monster of an example. So let me just show you what we're trying to do. Actually, let me start running the code because it takes some time as well. And while the code is running, I will open one of the web pages and I'll show you what we are doing. So let me just run all the code. I'll leave it in the background running, and in the meantime, I'll just explain to you what we are trying to do. So let me open this in a web browser so I can show you again what we are dealing with. Oh, sorry, it's getting a bit confusing, but the other thing was our actual code running. So this is what we are looking at. This is the data that we're trying to get. So this is the ATP website. No, this is the men's professional tennis ranking. So the ATP, which is the Association of Tennis Professionals, have a lot of stats about the different players on their website. So as you can see, we're dealing again with tables. So the initial thing we can do is the same thing that we did for the Wikipedia page. We can just get we can just get the table and get all the information in it. But this time we are doing a few things that are more complicated. The first really cool thing we're doing is if you scroll down to the bottom of the table, you can see that the web page by default loads the first 50 players only. So if you want to get all the players, you have to click this load more button. When you click it, you get everybody. Now, if we were sending a request to this web page via import, we're only going to get the first 50 because we have no way of telling the server, hey, can you please click on that button for me and then give me back the web page? That's pretty much impossible to do with import. But since we are automating a web browser, we can locate the load more button and we can click on it. And only after we've clicked on it, um, you can we can get the information, the full information that we want, which is all 80 players in this case. So that's one of the cool things we are doing in the code. The other thing we are doing is that there is not just one table, but there are three different tables. So we have stats for serves, we have stats for returns. So these are just different aspects of tennis if you're not interested in tennis. Um, and finally, we have under pressure ratings. Um, what we want to do with our code is because we want to, let's say, we want to compare some serve stats and see how they correlate with some return stats, or we want to see whether people who are better under pressure are better servers of the ball and things like that. So essentially, we want to combine all of this information that the ATP have on different tables. We want to combine it in a single table. So this is basically what we're doing in our code, which again is way too long for me to go line by line with it. But the basic idea is um, actually the only thing I do want to show you is how do we click on the load more button, because everything else is pretty much string cleaning and parsing text and kind of wrangling text to make it in a nice Wolfram language format. Um, but here when we open one of the web pages, we are looking for any element whose text is load more. Now, ideally, hopefully, there should be only one such element on the web page, and that element is the button. So once we locate that button, we can store it in this variable called load more button. And then once we have it there, we can call web execute with the following option, click element. And click element goes to whatever you want to click on the web page. In this case, we want to click on the load more button. I'm using first here just in case there are multiple elements in load more, but I think for these web pages there's only one, and it's our button. As I mentioned, everything else is pretty much string cleaning, um, dealing with data. Um, Again, we're doing interpreters on our country. So let me just show you what the final result. Once we have collected all of the data from all of the pages on the ATP website, once we have clicked all the load more buttons so we can get all of the players, and we have put everything together, this is what it looks like. Um, it is a tabular object which contains 100, the top 100 tennis players, men's tennis players in the world. And for most of them, you have the full information for um, each of the different statistics. But the cool thing now is that you have them in a single table, in a single tabular object, and their countries are actually entities again. So if you want to do any computation with any of the properties of the entities, you can do that as well. Because this is quite a big workflow to get all of that data together, I have saved it in a local file. So if you just want to explore the data um, without actually going through the whole web scraping part, you can just import the data from here, and hopefully that should get you the same object that we have. Oh, actually, it doesn't include the countries. Oh, in that case, maybe I should export this one because it's more complete. Um, but anyway, whether you get it from the local file or you get it from your web scraping, once you have the object, again, tabular object, very, very fast, very nice. You can do a lot of things with it. So let's actually start doing some interesting things with it. Let's see which country has the most representatives in the top 100. So you can see the United States has 14, France has 11, Italy has 9, and so on. There are quite a few countries with just one representative in the top 100. Let me know if you recognize your country. Um, let's do some other things. So let's see. As I mentioned, um, the ATP contains statistics on three different dimensions: serves, returns, and performance under pressure. So one thing that might be interested to see is to find a player with the biggest discrepancy between their world ranking and their serve ranking. So if we look at what our table looks like, so every player obviously has a world ranking, which is just their main ranking, and they also have a serve ranking. So as you can see, obviously people who are the best in the world are also very good at serving, because serving is such an important part of the game. So we want to see who is the player that either serves very well but is very low in the ranking, or is very high in the ranking but doesn't serve well. So this is a simple piece of Wolfram language code that we can execute to get that information, and we can see that Nicholas Jarry is ranked number 96, but he is the 13th best server in the world. So even though he is in the top, let's say top 15 for serves, which are a big part of the game, um, he is only ranked um, number 96, which suggests that maybe he should work on other parts of his game. Um, Find players who can serve really well but can't return. So we are looking here at the biggest discrepancy between serve rankings and return rankings. So Taylor Fritz is number 1 by serve ranking, but he's number 37 for returns. There are people who are really good at returning, but not that good at serving. So we're just looking at the people with the top 3 people with the biggest discrepancies between these two statistics. And then finally, we can create a nice manipulate object where all of the data in our dataset is made available via these interactive menus, and we can plot the correlation between any two factors immediately, and see what that looks like. And the points on the on the manipulator little tennis rackets, which I was developing this example on my MacBook, and I actually specified a tennis ball as the emoji for the plot markers. And only today I realized that on Windows, the default font doesn't include a tennis ball. It automatically converts it to a tennis racket, which is very interesting. If anyone is using a MacBook, I would be curious. I think if you open this notebook, you'll see tennis balls. Um, Obviously, not very important, but I do think the scatter plots look much nicer when the plot markers are tennis balls and not rackets. But anyways, that's not the main point. The main point here is that you are able for each of the factors, which now that we have combined all the tables, we have pretty good list of different factors that we might want to explore. So this allows us to do that. Okay, cool. Before I get into that, let me just answer some questions because Ro is asking great stuff so far. If you're taking any questions, is it worth pursuing web session execute, JavaScript execute, and why? On a similar note, is it possible to obtain our network data and mimic it using Notebook Assistant? So thank you for the question, Ro. Actually, I can answer the first part of your question because this is what we're going to be doing now. We are going to be doing JavaScript injections. So it is definitely worth pursuing because there are some things you can do with JavaScript that you are not able to do just by locating elements and clicking on them. So actually, let me show you what that looks like. Oh, I can show you kind of again a very simple example of why you might use it, but hopefully that gives you some ideas of the types of things you can use it for. Um, yeah, so Glenn is saying that he sees tennis balls instead of rackets. Yeah, I think the plot looks much nicer uh, with tennis balls, but anyway, again, not the most important thing. Um, okay, so we have looked at the basic functionality of automated web browsers. Basically, 90% of the time, you'll be opening a web page, you'll be locating different elements on it, and you'll be extracting. You'll either be extracting things from them, like their text, or you'll be performing actions on them, like clicking on them. There's several other things you can do. If there are any forms on the web page, you can input text and submit the forms. There are a few other things you can do, but they are all kind of very similar. And I mean, it sounds simple enough, but as you can see, just even that simple set of functionality um, gives you a lot of power, makes a lot of things possible. Um, in some cases, we might want to take it a step further. So, as I was just mentioning when I was answering Roll's question, there are things that you cannot really do um, even with the. There are things you can do on web pages just by locating elements and clicking on them. So I'll show you. I'll show you one example where we need JavaScript injections, just to show you something that we couldn't do if we were just using web execute. So let's start our session as normal. So what I'm going to do again is have my web session on the right because this is quite a cool example just to be able to observe. Web session on the right, code on the left. The first thing we do is fairly simple. We navigate to a web page. In this case, it's the Wolfram Language example repository. Um, so what are we going to do on this web page? Well, we are interested in the examples on the repository, and each of the examples on the Wolfram language example repository have authors, so the person who contributed them. Just a quick aside, if you're not familiar with our repositories, there are these resources that are maintained by Wolfram, but any Wolfram language user can contribute resources to the repository. So in the case of the example repository, if you have a really cool example in your Wolfram language code and you want other people to see it, you can submit it to the repository, and once the Wolfram team has reviewed it, it will be available here. So essentially, what we want to do is we want to see which people have contributed the most examples to our repository. Now, there is a slight problem with that. So let me show you. I'll open a new window. Um, Actually, not here. I'll open a new window because I don't want to mess the one up that is being controlled by our code. So let's open it here. So there is a problem. So we see a list of examples, but this is one of the web pages where once you scroll to the bottom, it loads more examples. So because we want all of the examples, we need to be able to scroll on our web page. Now, web execute, as nice as it is, there is no option to tell it to keep scrolling down until it has reached the end of the page. Like, such functionality just doesn't exist. So in cases like this, we can inject JavaScript code directly into our browser, directly into the browser that we're controlling via code. Um, a quick word on JavaScript. It's kind of the most. It's JavaScript is a language that's used a lot in web development to add functionality, to kind of act on the HTML, add things to it, remove things from it, and so on. And we are able to, once we have a browser that we're controlling via web session, we are able to execute any piece of JavaScript code in that browser. So in this case, we want a JavaScript code that will do what I described, a JavaScript code that will scroll to the bottom of the page, see if new examples come up. If they have come up, keep scrolling until it has reached the end of the page, so until it has loaded all of the examples. I'm not going to go through each line of the JavaScript code. It's not really a JavaScript webinar, but I can explain to you what it does. Well, it scrolls down, it locates each exam e- each example element, and it appends the link to a variable. And once that is done, it pushes that list to the HTML, so that once that list is pushed to the HTML, we can get it with our normal web execute syntax. So let's do that. Let's evaluate this JavaScript injection just to see what happens on the right. As you can see, I'm not doing anything, and the JavaScript code has scrolled to the end um, of the web page, and hopefully it has loaded all of the examples, and um, it has pushed them to an HTML element. And because we control what that element is called, we can give it a specific selector so we can very easily retrieve it after that. Um, this should be more than one object, hopefully. Let me see. Okay, so we have 260 examples. Once we have those examples, again, we can do our usual string cleaning. Here, again, we have a helper function, which is going to navigate to each one of the 260 examples and get the authors. So again, I'll let that code run for a little bit, and we can kind of watch it do its thing on the right while I kind of explain to you what it's doing. So with the JavaScript, we were able to get the hyperlinks of all 260 examples on our repository. Um, and because with JavaScript, we're able to do things like scroll to the bottom of the page, check if new examples have been loaded. If they have been, keep scrolling and repeat that over and over again. So this is an example of a kind of a slightly more complicated functionality that we wouldn't really be able to do just with simple kind of HTML parsing or even with web navigation. So I think it's a nice example to show a use case for JavaScript injections. But JavaScript injections are extremely powerful. You're basically able to run an arbitrary piece of JavaScript code in your browser. So it could be for things like scrolling to the bottom of the page, but it could be about manipulating the page, inserting content from different sources, all sorts of things. Once you're able to execute JavaScript, basically there is no limit to what you can do to your web page. And even though in this example we're using it for something fairly simple, um, again, I encourage you, especially if you're not really familiar with JavaScript or what it does. I do encourage you to look into it. And chances are, if there is something you want to do on a web page, but you're not quite sure how, and the basic methods such as navigating, clicking, locating elements, if the basic methods seem insufficient, then chances are that JavaScript will come to the rescue or can come to the rescue. You have to be a bit kind of more creative with it. So in this example, I mean, the scrolling part of the JavaScript code is just very easy. But how do we actually collect all the links, for example? In this case, I had to create a new element in the HTML. And once the JavaScript has collected the links, I told it to push it to that element, because with web execute, we can access the HTML, but we cannot access the internal JavaScript commands. Okay, so it looks like our little function has finished. It has traversed all 260 functions while I was explaining all of that to you. So let's look at what we have now. We can delete the object. We no longer need the browser, and we can do some final piece of string manipulation, and we can tally up all the contributors to our example repository. And we can see that Wolfram staff leads the way with 99 examples. Second one, this is quite interesting. Mr. Stephen Wolfram himself is the second biggest contributor to the example repository. Then we have the Quantum Computation Framework team, uh, who do very good work, very interesting work. I encourage you to look into their stuff as well. Wolfram Research, just different branches of the Wolfram teams. And then we have some actual individuals that have contributed 3 examples, 2 examples, and so on. And we have their name here. Thank you for contributing to the example repository. But yeah, I think this is pretty much it. So between simple HTML requests with imports and URL read, asynchronous requests with URL submit, and automated web browsers, you pretty much have all the tools you need to kind of build up your own workflows for virtually any website that you're interested in. Now, the main advantage of doing that in Wolfram language compared to any other language is that once you have the data, you are able to use any of Wolfram languages more than 6,000 functions to visualize it, to manipulate it, to clean it, to present it, to upload it somewhere, to cloud deploy it, and so on.